Hello, everybody. Thanks for making it to the bonus content. This is a visual model of the ambiguous case. I did not create it. Looks like the author was somebody named Jerome A. White. And this is a great activity just if you are interested in figuring out, well, what does it really mean to have an ambiguous case? This is a visual model that will explain it to you. This model is used for small side, long side, and a fixed angle. What you'll see is sort of like a pendulum swinging back and forth. The side for length of A is always 3. The length of B is always 9, and this angle of 30 does not move. It is stuck and measured from this baseline to this blue terminal side. That's how we get the 30-degree angle. We can adjust these with our sliders, but I'm not going to do that. This is an animation. The directions, the person who wrote this said adjust the value of A until it's long enough to form one triangle. Keep on lengthening side A until there are 2 possible triangles, and further so that there's only one possible triangle. We're not going to follow these directions specifically. I'm actually going to turn this off. What I am going to do is sort of lengthen this and explain why the ambiguous case exists. The ambiguous case happens when we have a small side across from an angle. We have, in order, small side, long side, and fixed angle. I can't increase this length. I can't increase the length of B. I can't increase the length of A, and this angle stays the same. These things are stuck, okay? Now, the value for the angle of C, it could be bigger or smaller, and that's what you see when you see this pivoting. The pivot point is C, that vertex, and you'll see that the side length is pivoting back and forth. It's not coming into contact with the baseline. Of course, if it did, we'd be forming a triangle. This would be a case with these measurements that no possible triangle can be formed if we did your law of sines. The directions did say that we could explore what happens when we increase or decrease this length. If I decrease the length, there's no way that this point is getting closer to this baseline. Even if I animate it, you'll see that it just swings back and forth but does not get closer. The closest it is to the baseline is probably like right down here, somewhere where it's like perpendicular to the baseline. That might be interesting to understand. If I keep lengthening it, there might come a point in time where if I swing it back and forth, it might hit all the way at the bottom, but it does not. I can increase it in such a way that now look what happens. It hits that bottom line, this point at the end of this length. It hits the bottom baseline in 2 locations. And I can try to pause it exactly when it does that. This is still a small side, long side, and angle. What you'll notice is that there are 2 values for the angle of C. Angle C can go from here all the way across, and that would be your first triangle, this large triangle where I stopped the side length of A from rotating. That would be the first case. In order to do this, what you need to do is use your law of sines to find your angle B. This is the first one. This first angle looks acute, opposite your 90, because sine inverse will always give you an acute angle in quadrant 1 when your ratio is positive. What you'll notice is if I swing this point across to the other side, we're going to have to try that again. If I swing this to the other side, when it contacts this point, we're just going to say close enough, it comes in contact with this other point at B1. Okay, so what I do notice is this side length is also 5.2, so was that. What I have here, this light triangle, is an isosceles triangle. Now, we don't know if it's equilateral, but I do know it's isosceles. At least 2 of the sides are the same measure. That would mean the value for the internal angle at B2 is the same as this external angle at B1. It's external to this smaller triangle inside here, formed by A, B1, and C. But what's the relationship between the internal angle B1 and this angle inside the other triangle? If this angle and this angle are across from sides of equal measure, these 2 base angles are the same. How do we find this angle? Well, if this angle measure over here is one of the angles that form a linear pair, then this other angle must be the supplement. That's why in our lesson we use the supplement to find our second value for B. So one of the angles that we find when we do a sine inverse is this one. And when we take its supplement, we're determining if it's possible to form another triangle using its supplement. If all 3 of these angles are less than 180 or exactly 180, then you have formed this triangle. If for some reason it's too large, we only have one triangle possible, its supplement wouldn't work, then the math would indicate that. So when do we get just one triangle? If this was shorter, we don't get any. If it's longer, we get more than one. Let's see when we get one triangle. Okay, it has something to do with this. When that side length contacts the baseline at a 90-degree angle, pivoting it left or pivoting it right using the pivot point of point C, or vertex C, that will get it farther away. There's no, if I animate this, there's no pendulum swinging. This is the only point, the only way that this side length will contact it if it's perpendicular to the baseline. So this video essentially describes when there's 0, 1, or 2 triangles possible using the ambiguous case. Again, that happens when small side, long side, and angle, because there's no sSA congruence property. Now the directions said something like, you know, rotate it, rotate it, rotate it, then rotate it some more until you get just like one triangle. Okay, so now there's only one triangle. But if I pivot this point, there's only one triangle that's formed. So there's some sort of maximum length that eventually this triangle will only be possible. One triangle will only be possible again. And you know what happens? Think that happens at exactly 9. A little bit less than 9, equal to 9, bigger than 9. Then we don't have the sSA anymore. We have long side, little side, and angle. That's only one triangle, not ambiguous. Thank you for watching. Hopefully that clarifies a couple of things. Move on to your homework. It is in Delta Math tonight. Thank you. Have a good day.